Um, those of you who took chemistry somewhere before, you remember the word redox reaction. Did you like redox reactions? You did? I always expect people to go, no, I hated that, because it's kind of a deep dive. But we've gone over, well, let me say this. If you have, do something simple like well, let's just do this. Cl plus Na. So what happens to a Cl to make it negative? So this is, we already know this, that's Na plus and Cl minus. They come together and make NaCl. All right, so what happens to Cl so that it can do this compared to this? What is it? Gains an electron. So it has to get an electron from somewhere to form this, and then it can be attracted to something positive. We know Na to become this, what does it do? To become positive? Loses an electron. And what I'm saying is, if I call this a reaction, this electron is really this electron. I mean, sometimes during a reaction, an electron actually leaves one atom and goes over to another atom, and then resides over there. So this is sort of an elementary electron transfer reaction. But I don't get hung up there. This goes better if I just start telling you. So reactions like, not all reactions have an electron transfer. The ones that do are called redox reactions. It stands for oxidation reduction. And I'll tell you what that means in a minute, but I want to show you the reactions you've seen. Okay, going back to information from test 1, this reaction where calcium comes off and it goes with here, CaSO4, and then the Cl and the Li go together. So we call that a double displacement reaction. It turns out this whole reaction where you get Ca plus, is this balanced? So the Ca comes off just the way it went on. It went on after it was already positive, and the Cl went on here after it was already negative. You get these ions that split out, and then they rearrange and go back together here. There's no electron transfer going on. So this is just called I guess we just call it a precipitation reaction, double displacement reaction. But when you have an electron transfer, it's not always obvious by just looking at it. So we have to go through this kind of tedious process to figure it out. And the first subject really, I'm just trying to get to this, is so oxidation numbers, oxidation state, those are synonyms. It's kind of like we say freezing point and boiling point. I don't know why we say point, because we always want temperature. Freezing temperature, boiling temperature. Oxidation numbers, oxidation state. it's really kind of a charge we're thinking of, the oxidation number or the oxidation state. In most cases, it really is just straight up charge. In a few situations, you just kind of have to do this little bookkeeping game by a set of rules that they're not really going to have any logic to you. But it's not as bad as it says. There's a list in OpenStax, and I added on the, anybody download the PowerPoint before today? I try to get them up before class anyway. There's an extra page in there from another book that has these rules that I think is a little more better stated than the OpenStax book. But let me explain to you what's up here, what each of these arrows is saying. If you have an elemental compound, and that means any of these, H2, N2, O2, sulfur exists as S6 sometimes. This means carbon solid. H2, N2, O2. I've left off there all the halogens, F2, Cl2, Br2, I2. What else is over there? Carbon. This with the S in it means it's a solid, so I include it there just because that's the way it's written in a reaction. These depend on, sometimes they're solids, sometimes they're, I think all of these are gases. I think Br is a liquid. Iodine, I think, is a liquid too. That's not as important. It's just this S. Carbon solid. I think the S6 is solid. So I'm just bringing these examples, not something to memorize. If you have metals, like Mg, and it's not in an ionic compound, and it will never be in a covalent compound. I told you guys before there's metallic compounds, but they don't come up very much. But if you see a metallic compound, it will have the S on it too, and that's a solid chunk of magnesium. That might be too reactive as a good example, but let's say copper, any of the transition metals. That's why I got this, because I knew I would think of them. If you have chromium as a solid, what else? Zinc is a solid, you can have as a solid. Iron is a solid, so if you had a big iron bar that went clang, that's the way we would write it. Iron with an S in it. All of these, its oxidation state is 0. Elemental just means there's only one type of atom in the whole thing. Of course that's true for all of these. Really, this is just a big mass of a bunch of carbon atoms. This is just a big mass of a bunch of sulfur atoms, or S6 atoms. And this is just a big mass of metal together. So it's either these or these, and any other transition metals you can think of that you might put an S on just because it's all metal. Those all have an oxidation number of 0. So there's your first rule. And then, easier to explain is, if it exists as an ion, anything we've talked about, or at least the monatomic ions, not the polyatomic ones. I listed a few here, but I won't even list any. It's just any of them we thought of, we talked about already. Like, if I said, what's the charge on fluorine, you'd say -1. What's the charge on oxygen, you'd say -2. What's the charge on lithium, you'd say +1. In those cases, that's the oxidation number for those. Because this is mostly about charges. So there's your second rule. If it's a monatomic ion, it's just the charge that's on it. The oxidation number for magnesium is 2+. Do notice the difference though. Let me say, if you see that versus this one's oxidation number is 0, this one's oxidation number is +2. That's why I was stressing the S. So there's copper +2 as an ion. That might be aqueous, depending on what you're talking about. But this is a solid. Aqueous means it's dissolved in water. But this one's definitely +2. So contrast those two. Ions are just the charge that's on them. That's the second rule. We kind of get into the weird rules here. These are kind of the iffy ones. Hydrogen, when it's connected to a non-metal, its oxidation is always +1. And hydrogen, when it's connected to a metal, it's always -1. Exactly why that is starts to get a little nebulous here. So I won't go into it. It's really kind of just a bookkeeping thing to help us find when a reaction is a redox reaction. The other weird ones here are these two here about oxygen. Almost always oxygen is -2, which happens to be the same charge it would have. The weird situations, I think if I brought up any, it would just be this one. H2O2 is called peroxide. In that case, oxygen will have a -1 instead of -2. But I know if you don't have experience in chemistry, it's hard to look at something and go, oh, that's a peroxide. And then fluorine has a special role with oxygen. If it's fluorine and oxygen connected together, oxygen will actually have a positive value, but it varies depending on the situation. But there is a way to figure out. We end up inferring what it is. So these are all about oxygen. Just put oxygen. There it is. And then this one that I made with a bigger arrow. SO421. If you take all the oxidation numbers and add them up, put up here, CTH6. So I find the oxidation number on these oxygens, and I find the oxidation on the sulfur. They all have to add up to whatever this charge is. Over here, there's no charge. So all the oxidation numbers for these in this compound have to add up to 0, because this is technically a 0 there. That's what this last rule is stating. Once you enumerate all the oxidation numbers, they have to add up to whatever the charge is. So this is a molecule, but happens to be charged, so we call it a polyatomic ion. This is a covalent compound. It has no charge. But all of these oxidation numbers for the 2 carbons and the 6 hydrogens will add up to 0. There'll be positives and negatives, and they'll cancel each other out. Those are the rules about oxidation numbers, oxidation states. But it really helps to see it in action, which is why I'm kind of trying to get past the rules. I put, if you look at the PowerPoint I put up today, I put up 2 of them. Y'all know how to get to the PowerPoints on here? I think you have to click content to get to them. So Monday, March 2nd, it is the second one. So this is the main one that I've got in my hand. This is one that I made a long time ago that just has a bunch of examples in it. But I'll go through the examples on the board. But it's written such that you can read that PowerPoint on your own and understand what it's saying. But that's what I'm going to go over now. Over that. Oxidation numbers. So the first skill to know to deal with redox reactions. There's a page in here where I have just a bunch of different compounds. And I'll show you how this works. So you've got a reaction, you've got this plus this, arrow, this plus this. Well, let's say one of the things, reactant or product, is that. All right, the way you find the oxidation numbers, this one is going to look very familiar. This is tin. It's one of the transition metals. Actually, it might be post-transition metal. But a few weeks ago, if I said, what's the charge on oxygen? What would you have told me? -2. And like I said, it's almost always -2, so just kind of start there. Unless you see H2O2, then it's going to be -1, and that'll be the rules for us for oxygen. And I would have told you, there's 2 of them, so it's oxygen 2 negative, oxygen 2 negative. That means you've got -4. Up here, there's no charge, so I'm going to put a 0 here. Now, what do I need to put here to make this true? +4. There's only one 10, so it must be 4 plus. So in this case, the oxidation number on oxygen in this compound is 2 minus, and for 10, it's 4 plus. And those do add up to 0, the charge on it. That should look familiar. Okay. Now what if I had this? This is called bromate. It may or may not have been in that list of polyatomic compounds. It probably had ClO, ClO2, ClO3, ClO4. Hypobromate. Anyway, we won't go back to naming. But if you just replace the Cl with Br, it's this. But what if I said, what's the oxidation number on all of these that are there? The first thing you want to do is recognize that as one of the polyatomics and pop the K off. K plus. If this is neutral and I pop this off and this is plus, what does this have to be? It's 1 negative. All right. So you've identified 1. Plus 1 for K. Now look here. You've got 4 oxygens. Assume it's -2. -2, -2, -2, -2, because there's 4 of them. We have -8 equals, and I'm going to bring this down here, -1. So that's the twist from what you saw before. So what has to go here for this to be -1? +7. So Br here, 7 plus. So for Br, it's +7. For oxygen, it's 2 minus. And this is the last positive charge we would need here to make this 0. So these all do add up to whatever the charge was here. This didn't have a charge. OS is osmium. What's the oxidation number in all of these? Again, you start with the same strategy. You pop the K off, but there's 2 of them, so go K plus, K plus. It's +1. And we're left with OSO, so what's the charge need to be here? You got 2 plus 1, so you need this to be 2 minus. And now you do that game again. There's only 1 oxygen, so it's -2. And that's 2 minus. I'm going to have to subscript off of that one. Skip that. Just made that up. There's 4 of those. That should be +4. Because it's the easiest way to get to the answer.
Okay.
You pop the, if there's 3 of them in a row like this, what's the one paper for?
Can you only do that if there's K?
Huh?
Can you only pop the first one up?
Yeah, this is one of those polyatomic ions. So if we were still talking about ionic compounds, actually, I'll just go ahead and do this as Cl, because that was on your list as polyatomic ions. If you can recognize that as a polyatomic ion, then you know what's going on here. You learned it already a few weeks ago. You've got K plus and ClO4 minus. That's why you pop it off, because this rule that says the charge that it is its oxidation state. So you can go ahead and get to this one real quick, because that's the charge, plus 1 is the charge on K. And this is a polyatomic ion.
Okay, so if there's a polyatomic ion, you can
Yes.
separate it first, but it doesn't have to be K.
No, it doesn't have to be K. You're right. Any of those first columns, there's such thing as KClO4, IClO4, and then if I go to the +2 ions, MgClO4, 2. I guess I'll do one of those. Al2, 3, so we'll do those two next. So, what are the oxidation numbers for this? If you recognize that as a polyatomic ion, you know you can pop the Mg off, and it's 2+. You have ClO4, ClO4, and that tells you both of those are negative. That's kind of a review. There's 2 of these, so if I split them apart into their ions, I have this ion and these 2 ions. You with me?
The bottom would be adding -2.
Yeah, we'll play the same game with this. But just while we're here, realize I have a monatomic ion, so I've determined this one. This one's 2+. And then I'll continue with ClO4. These are the same, so I'm just going to do one of them. Minus. And now the rest is like I did before. -2, -2, -2, -2, -8. There's a 1 there. So what does this have to be for this to be true? +7. There's only 1 Cl there, so it's +7. So 7 plus and 2 ones. And I only had to do one of these because they're identical. So every oxygen in here have this oxidation number. Both chlorines here have a +7 on it. See what I'm doing? It was K2OSO. It didn't show up on my OS4. I'll go back to that one. I just show that process in here. I want to get to more of these with polyatomics. But you could look through here, and I'll come back to that. Okay, oxidation numbers for Al2, ClO4, 3. chlorine, we've got oxygen. What's the oxidation number on each one? Well, the first thing you want to do is go, that's an ionic compound. I'm going to pop off the two aluminums. What's the charge on those two? Yep. So we got that one, 3 plus. We've got ClO4, ClO4, ClO4. If there are 3 of them, and they have to total 6 together, maybe I should do it like this. That is plus 6. There's no charge up here, so that's 0. So what has to go here has to be minus 6 to make that 0. If I split that minus 6 up, that's minus 2, minus 2, minus 2. And I'm not there yet, but now I could just take one of these and work with it by itself. ClO4, 2 minus, minus 2, minus 2, minus 2, minus 2. I've already done this process. Minus 6 equals minus 2. So what is Cl here? ClO4 is minus 1. I did this wrong. Sorry. That's the formula for aluminum perchlorate. Pop off the aluminum. 3 plus, so that's 3 plus. We have 3 of these. They have to total 3. There was no charge up here, so there's a 0 there. So this has to be minus 3, and then there you go, we'll have like that. I changed this formula. It's Al, 1 Al, and 3 ClO4s together. I'll do this one more time, but I've done the same one several times now. So if you've got that, don't forget this up here. It's negative 2, negative 2, negative 2, negative 2 for the oxygen. Negative 8. This means negative 1. And plus 7. There's only one Cl there. This is plus 7. I think in oxidation states we put the sign in front of the number, but it's okay, you know what I'm saying. Okay. Let's do this osmium one. My copy didn't take a long time before. Osmium. Just to get away from K, let's do sodium. Na2OSO4. Recognize it as an ionic compound. So this has to be 2 minus on there because of these 2 plus. So we've already got plus 1 for Na. 4 oxygens, minus 2, minus 2, minus 2, minus 2. This is seeming really redundant. Plus 7, so the OS is plus 7. So plus 7, minus 2.
Wait, why is it minus 2? We're going to do,
Say again?
why is it minus 2?
Why is this minus 2?
No, at the bottom, at the bottom.
These?
When we're doing to the equals negative 1, why isn't it equals negative 2? That's the triangle.
2 negative. Those should have all been. Did I do K2OS4? Yes. No, that's right. If I had K2OS4 up here, So this is at ClO4, which was -1. This is the correct formula. Na2OS4. Let's start over. Before I had Cl here, ClO4 was 1 negative, but OSO4 is 2 negative.
Yeah, so when you add the bottom, it should be 8. -8 equals.
-2. Did I have 1?
Yes. So it should be equal to
Okay. Na plus OSO4 2 minus. Okay. -2 minus 2 minus 2 minus 2. -8 equals -2.
Okay.
Okay.
Yeah.
Yep.
Thank you.
Okay. Yeah. Okay. Good.
Thank
It's something different finally. All right. So what do we need here?
you.
Plus 10 minus 8, no. Plus 6. Okay, so osmium, there's only one of them, so that whole charge goes up there. This is plus 6. Okay. I don't think they get trickier than this. When I start doing reactions, though, we'll be looking for these to have the zeros and the charges on them, and then we'll deal with the oxygen. I have examples over here. No, I don't. I have examples over here. And there are examples in here too, I think. But I'll leave that just for extra review. That you can download, but let me go through the examples I've got here. Generally, you can pop off what's on the front. PO4 is in that list of polyatomic ions. Hydrogen. Hydrogen with nonmetals goes +1. Hydrogen with metals goes -1. What are these? These are nonmetals. So what's the charge on the hydrogens? +1. We're here. H with nonmetals is +1. These are nonmetals. So we've got H plus, H plus, H plus. You follow that? So your strategy is to pop those 3 hydrogens off. And we already got that now. It's +1 for the hydrogen. PO4, 3 minus, -2, -2, -2, -2, -8. Bring down the -3. So what does this need to be?
But why is it 8?
There's 4 oxygen and it's 2, 4, 6, 8. So -8.
That's
5 plus 5, yes. There's only 1 phosphorus, so it's 5 plus. So we got +5 for that. It's still 2 minus oxygen. I should say -2. Those are the oxidation numbers for the atoms that are in that. Now with me. OH is a polyatomic ion in that chart. You want to pop the aluminum off here. So you already know the charge on aluminum, which is and then you have 3 OHs, and each one of those are -1. So I'm going to just take one of them. I'm going to go OH, -1. All right. Hydrogen with a nonmetal has what charge? that's plus. And then what is oxygen usually? 2 minus. It's not a peroxide, so like I said, it's almost always going to be this. And if you add those together, you do get -1. So now you've got it. 3 plus, 2 minus, plus 1. Not being consistent. Let's see, plus 3 and minus 2 is minus plus 1. You with me? It is just best to go through a bunch of examples. Huh? This one is aluminum, was 3 plus. Oxygen was 2 minus. And hydrogen is plus 1. Or 1 plus. I'm not doing oxygen. Yeah, if we add those up, it should equal -1. Or no, it should equal 0. This was plus 3. These together add up to -1, right? And you have -1, -1, -1. I mean, these aren't going to add to 0 up here. But after you multiply them by how many are there, they'll add to 0. You've got 1 Al, that's 3 plus. Plus 1, 2 minus, 2 minus, 2 minus. Plus 1, plus 1, plus 1, minus 2, minus 2, minus 2, plus 3 should equal 0. Six minus, 3 minus, 3 plus, 2 plus. Yeah, that's right. Plus 6, minus 6. They do add up to 0. Double checking never hurts, especially when you're me. Oxygen, not a peroxide. -2, -2, -4 equals 0 because there's no charge here. So this is just like doing ionic compounds. So this has to be plus 4. So the selenium is 4 plus. Let's see, plus 4 minus 2. Did I lose you? The plus 4. So I've got 2 oxygens, so it's -2, -2. So I've got a total of -4. There's no charge up here, so I'll put a 0. And then I go, okay, what do I put in there to make this true? And it's plus 4. And there's only 1 selenium. So that whole plus 4 goes on here. That should look familiar. It's the same way it had you determine charges on transition metal. Say again? Yeah, you've got 2 of these -2 charges and 1 plus 4 charge. So it does add up to 0. I just write it here, I only write it once, but there are 2 oxygens here. But every oxygen here has this oxidation. So I just wrote it once. But there's 2 oxygens, so there's a total of -2 -2s. There's like 1 selenium, so there's only 1 plus 4. See what I'm saying? It does add to 0. This is showing that it adds to 0, actually, this part. It has to add up to whatever the charge is, and this charge is 0. So. How about this one? Indium 2. Don't we do that with our rules? Oxygen. And then get some sulfur in there. Let's see if the other both mentions it. How is your hydrogen oxygen?
Okay, I'm slightly confused the last one, we did the SE02.
Well, I'm confused on this one, so let's skip that one.
Okay. For the SE02, you got a charge of plus for doing. So are you only looking at the charge? Okay, so I'm trying to figure out how to ask this. It has a charge of plus.
The charge on a monatomic ion, let's say selenium, it's just the charge that's on it. But selenium could have other charges. So I'm keying in on oxygen here.
Okay, so you're just trying to match selenium to whatever the charge is of oxygen.
Yeah.
Because there's
This
two
was
oxygen
-2,
that's -2.
-2.
So you're just trying to kind of.
I am looking up here, seeing what the charge is here, and it's 0. And then I'm going to here, what does this have to be?
Okay.
And then kind of key here is there is only one selenium, so that +4 has to all be on the one selenium. If there were 2 seleniums, then I'd say I'd split it up, +2, +2. But there's only one, so it's Se4+. There is a rule on sulfur, but I don't remember it. It's not in this book. It's not in that other book I used either, so I guess we'll skip that. Okay, let's try to do something with these, because I don't think we go in any direction. There's not a rule to follow for that one. Not hidden by this book, though. Okay. So let's try. Let's try to actually look at some reactions. Let's go. All right. In this context, like I said, we haven't talked much about the electron transfer yet. I just showed you how to find oxidation. But a key in these reactions are an electron comes off of something and lands somewhere new. If I add electrons to something, in terms of its charge, what happens? Let's say it reduces, right? I mean, if I have something that this does happen, it's, we have, let's say it's osmium, and it's 3+, and then something happens, and it becomes osmium 2+. That thing that has happened to it is it's gained an electron. And what I want to say is, what happened to its charge? It reduced. What's occurring across this arrow here is called reduction. But think in terms of the charge to help you keep these two straight. If you're adding electrons, lowering the charge. If you're lowering the charge, you're adding electrons. You're reducing the charge. That's called reduction. You with me? And to remember that vocabulary word, reduction. I'll say reduction. Just think in terms of charge. Is a charge going down, then a reduction is occurring, which is the same thing as saying an electron has been added, so it's reduction. The process of an electron being added to something is called reduction. We could have called it electron addition and avoided some vocabulary word. Chemists love their vocabulary word, so it's called reduction. So I key in on the charge, and I figure that's where that word originally came from. It reduces the charge. You would think losing electrons would be the opposite of reduction. It's not. We call that oxidation. Because originally people thought this could only happen with oxygen, so they called it oxidation. Years later they figured out it's not just oxygen, but they kept the word. But this is, of course, charge increasing. If you lose an electron, it gets more positive. And of course, let me leave it at that. But key words for redox reaction is reduction and oxidation. They have to happen together because something loses its electron. It's got to go somewhere. It doesn't just float off into the universe. So you got to have something that's being reduced while you're simultaneously having something that is oxidized. That's what they're called redox reactions. Both of those things are occurring in the reaction. All right. Here's a reaction. Okay, we're supposed to figure out whether or not this is a redox reaction. Example 4.6. So we're going to go about figuring that out. The first thing we're going to do is find all the oxidation numbers. Here we have zinc. CO3 is one of those polyatomic ions. Zinc is a transition metal. I lied to you when I said all transition metals can have more than one charge. There's a tiny number of exceptions to it. Zinc is one of them. But if you look up CO3, 2 plus, 2 minus, that 2 plus. Up here, take it. I haven't included this rule for y'all, but it might show up on the ACS file. I want to see it correctly the first time. Transition metals. Start right here with zinc from the right side. It's the very last one. The 3 that have definitive charges in the transition metals is these that make a backwards L. Zinc, cadmium, and silver. It's +2, +2, +1. There. Now you know all the rules of transition. All right. Zinc is 2 plus. Now if we follow this process, -2, -2, -2, I ended up with a bad one again. -2, -2, -2, because there's 3 oxygens, so -6. There is a charge here, -2. So what's this? Again, there's 3 oxygens, so I got -2, -2, -2, which add up to -6. I brought the -2 down, that's key, don't forget that. So what goes here? +4. So the carbon has to be +4, and the oxygen was -2. So this is +4, and that's -2. Do you see where I get these 3 numbers? Zinc was +2, carbon was +4, and oxygen was -2. And we have to do that with all of these. You with? I'm waiting for her. You got it? Oxygen with zinc, oxygen with a metal. No, almost always -2. Okay. We're going to do this. We're going to split these out and go zinc, 2 plus. So oxygen has to be -2, and that's typical of oxygen, right? A few weeks ago, if I said, what is this? You would have said an ionic compound. And then I would have said, what's the charge on oxygen? You would have said -2. And I'd say, so what's the charge on zinc? And you would have said +2. Right? -2, +2. Right here, there's no charge here. -2, -2, -4. No charge. So what goes here? This is +4, and this is -2. Asking the question, is this a redox reaction? We're looking for something to change. So zinc on this side is +2, zinc on this side is +2. It hasn't gained or lost any electrons. So far we don't have a redox. Carbon +4, carbon +4. Those don't gain or lose electrons across the arrow. And then oxygen, -2, -2. So nobody's gained or lost any electrons by these rules. Therefore, it's not a redox reaction. I wanted a redox reaction. So I just did the first one there. This one, I think, yeah, this one's going to be a redox. All right, that was A, for example, 4.6. Next, let's do 2 galleons. Okay, there's the reaction. I probably shouldn't have stressed this S so much when I'm going CDU solid and whatever. A few of these are going to be liquid. Like you probably know Hg is a liquid, mercury at room temperature. Another famous one is Br2 is a liquid. So it isn't just that it's a solid. I just told you to key on that. But gallium is the only element here, and bromine is the only element here. So what does that tell you about their charges, their oxidation states? Those are the elemental ones. Elemental just means there's only one type of atom in the whole thing. So this is a liquid sample of just gallium. Gallium happens to be liquid at room temperature. And bromine is a liquid too. Yeah, they put them both as liquids. So maybe I shouldn't have stressed solid so much, but it's kind of rare for this. It's almost always a solid. But the key is not the solid. The key is that there's only one atom here. There's only one type of atom here. That's what makes them elemental. They're completely homogeneous when it comes to atoms. Which means this one's oxidation state is 0, this one's oxidation state is 0. Because they're by themselves. Because there's only one atom there in the compound. There are 2 bromines here, but they're both bromines. There's only gallium here. Okay, now we go over here. If you looked at this a few weeks ago, you would have said, oh, that's an ionic compound. And I would have said, what's the charge on Br? Br does weird things when it's connected to oxygen. What's the charge on just one Br? You said it. -1. So -1 for that. If there's 3 -1s, what's the charge on gallium? +3. Okay, now we've got it. Going from here to here, and going from gallium here to here, has gallium gained or lost electrons? It went from 0 to +3. Electrons are negative, so it had to have lost 3 electrons. -3 electrons. And bromine went from 0 to -1. I'll just say lost electrons. Lost electrons. Bromine has gained electrons, or it's gained 1 electron. You see that? Based on this charge, if this was 0 and then later it was +3, it had to have lost 3 electrons to get there. And these 3 bromines, each one of them has gained an electron. So I'll say gained electron. If you just look at the charge, what happened to the charge? How would you describe what happened to the charge going from here to here for bromine? It reduced. Yeah. Reduction is occurring here. And like I said, think about its charge to get the vocabulary word. It went from 0 down to 1. It reduced. That means the other one oxidized. I'll say oxidation. Reduction occurred. It was reduced. Oxidation occurred. So another question you could get is, you could be told, hey, here's an oxidation reaction, a redox reaction. What was oxidized and what was reduced? And your answer would be gallium was oxidized going across here, and bromine was reduced going across here. You with me? One more twist. It is a twist, it's confusing. Something that can cause oxidation is a thing that can cause something to lose electrons. There's 2 things next to each other. One of them's like a vacuum cleaner, and it has this ability to pull electrons off of something. So something can cause oxidation, and something can cause reduction by shooting electrons towards it. This is confusing. Gallium, instead of it, I'm going to say gallium. Instead of it, I'm going to say bromine. Oxidation occurred on gallium. Gallium was oxidized. Gallium is the reductant because it caused reduction to happen by its ability to lose electrons. That is confusing because I'm just flipping that word right here. But that's the reductant, which makes this the oxidizer. or the oxidant. So reduction occurred to bromine. Bromine was reduced. Bromine is the oxidant. Bromine caused oxidation. It caused oxidation on the gallium. All those phrasings are used for these types of reactions. So that's just chemists wanting to make things more complicated. Caused oxidation. Gallium caused reduction to occur. So you might be asked the question, which one is oxidized and which one is reduced? And the next question might say, here's another redox reaction. Which one is the oxidant and which one is the reductant? And it could kind of screw with your head. So just to make it clear, all this type of verbiage is used. Things that undergo oxidation are themselves reductants. Things that undergo reduction are themselves oxidants, because they can cause. The ANT implies causes, and here we need causes on something else. You with me? So yes, the verbiage is confusing. Skip C on this. If you're looking at these later, and like, here's a really odd example. It's like, this is introductory chemistry. Shut up. Do you remember combustion reactions? You remember the word? That's really what I mean when I ask that. I don't expect you to come up here and explain it. But combustion happens when you have something like, it's almost always a hydrocarbon, but it could have oxygen on it, it could have nitrogen on it. But this is basically burning, flames, fire. But it's always consumes O2. This is always the same in any combustion reaction. This might be different, but it's always O2 here. And you always get CO2 and H2O. And I don't think I have this balanced. This was should be CH4. 2 there. These are notoriously hard to balance, except for CH4. Anything bigger than CH4 gets weird. I just feel the need to balance it. That's 4 of those. 1 carbon. Okay, that is balanced. So that's a combustion reaction. All combustion reactions are redox. But let's go through it. Hydrogen attached to carbon. Hydrogen attached to a nonmetal. What's its charge? Hydrogen with a nonmetal, that's right, so +1, +1, +1, +1. There's no charge here, so 0. So what goes here? -4. So carbon is -4, hydrogen is +1. This is for O2, I think it's still 2 negative. But just don't go around. Take that back. I can't remember these. Oh, duh. What is the oxidation number on O2? Good Lord. I start teaching at noon and I get tired on you guys. I don't know how I'm supposed to make it to 4:45. What's the oxidation on O2? What is it? 0, yes. Because it's elementary. That's not the first time I forgot that in front of a class. -2, -2, -4 for the oxygen, no charge. So this has to be +4. And that's -2. 0 is okay. +1 and -2. Wow. Oh yeah, it's the oxygen. But I'm missing something. Yeah, it's H2O. It's definitely H2O. I'm getting a change of oxygen. -2, -2. That's +4.
Is it because you have 3
Oh, yeah,
oxygen
yeah,
on
yeah.
one
Okay,
side?
I see it now. I should institute a break in here, but I'm not going to start again once I take a break. Okay, do you see it now? I see it. This was, so it was -2, and each hydrogen is +1 for oxygen. Hydrogen attached to a non-metal is going to be plus, so it's +1, and oxygen, as usual, is -2. Do you see what's different? +1, yeah, 0 to -2. I guess it doesn't matter which one of these we look at. Do you see it? Carbon went from -4 to +4. And oxygen went from 0 to -2. So which one's the oxidant? Which one is being oxidized? Which one? No. Which one is being reduced? Look at the charges. Which charge is being reduced? Oxygen goes from 0 down to -2. So the oxygen is being reduced. You see it? 0 down to -2. That's a reduction. And therefore, carbon is the one that's being oxidized. You see it now? And that's true in all combustion reactions. It's +1 in both places, so it didn't gain or lose electrons. You with me there? Combustion reaction. Yes. That one wasn't on here. I just decided I had to do a combustion reaction. Because usually you're introduced to those early on, and then when they come up later, they seem more complicated. How about this one? Next, who is it? Before I go on, what's the oxidation number here?
0.
0. That's elemental. Okay. 0. These are nonmetals, so what's the charge on H? +1. If I split that 1 H plus off, I have NO3 negative. That's in your list of polyatomic ions. So let's work with this. 3 oxygens, -2, -2, -2. We get -6. There's a -1 here. So what needs to be here? +5. There's only 1 nitrogen here, so that whole +5 goes on the nitrogen. +5 -2 for the oxygen. Here we're going to pop the Cu off. We have 2 NO3s. We already know that both of those were -1. So what's the charge on copper? +2. This is the same as these NO3s, so we're going to end up the same here, +5 -2. The copper changed, so something else is going to have to change. Let's look at NO2. There's no charge here for this NO2. So -2, -2, there's the oxygen, -4, equals 0 because there's no charge. So what's the charge on nitrogen here? +4. There's only 1 nitrogen, so we're going to put it there. -2. So the nitrogen was +5, now it's +4. The copper was 0, and now it's 2 plus. And we already did this before, +1, -2. All right. So do you see the changes? I already mentioned them. Copper here is 0, copper here is +2. H is +1, +1. Oxygen is -2, -2, -2. The changes in nitrogen. Those are +5, not that nitrogen. This nitrogen. All right. What has happened to the charge of nitrogen going from here to here? It has, but if you said about the charge, what would you say? It has gone down. It went from +5 to +4, so it has gone down. I'm trying to get you the word reduce. It reduced. The charge reduced. So this is reduction. Nitrogen is undergoing reduction, and that necessarily means this is undergoing oxidation. Which one is the reductant? Reductant. Huh? Copper. This is the reductant. This is the oxidant. Redox reactions. Should we do more of these? Huh? You say no? Let me just allude to this. This PowerPoint that says today's date, Monday, March 2, redox reactions. It's up there on D2L. It starts out showing this process that I've been through. You can look at these, just a bunch of examples. Yeah, I guess I should mention this. Somebody came up with oil rig. You hear that one before? This is a good one. I think of the charge goes down, it's reduction. That's how I remember it. But anyway, oxidation is loss, reduction is gain. That's of electrons, not charge. Here's a bunch of reactions you could try, but I go through them one by one in the next slide. So you can go through, I even went through the vocabulary, oxidize, reduce. Well, I didn't say reducer. The reductant is the reducer. The oxidizer is the oxidant. But anyway, you can look look at that for more practice to these. The other thing I have to do is that. You're gonna love this.
Can you, post the PowerPoint? I need working on it.
Isn't it there?
Yeah.
I swear I just downloaded. Oh, I left it. There, you should see it now.
Thank you.
Okay. One more thing to do, which is kind of a long walk. Did you balance redox reactions? Do you remember doing that? Do you remember it fondly? Nobody likes this. You can't tell me you enjoyed it, right? All right, you just took that and you wanted to balance it. The first thing to do is to split it into what we call, give you a list. Split it into half reactions. A half reaction is, you take the two things that are changing, like the Fe and the Fe2 plus and Fe3 plus. So the half reactions here are Fe2 plus, Fe3 plus, and then the other half reaction here is the Cr2O7 to Cr3. 2 minus and I guess Cr must be changing oxidation state. Let's see what Cr2O7 does. There's 7 oxygens, minus 2, 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 1, 2, 3, 4, 5, 6, 7, minus 14. I got a 2 negative. So it's plus 12. And then there's 2 CRs. So you split the plus 12, so that's 6 plus. So that CR2 starts out as 6 plus and ends up as 3 plus. I just had to check that. Make sure we're not going awry. So there's the 2 half reactions. You start there. So we want to balance everything except for any oxygen that's there or any hydrogens that's there. Fe is good because there's one Fe and there's one Fe, so that's good. This, to balance it, you've got 1 CR over here and 2 over here. So to balance it, we're going to put a 2 here. That's the next step. Next, we're going to add the add water next. So you see the problem here. We have oxygen here, but no oxygen here. We need to balance the oxygen over there by adding H2O. To get 7 oxygens out of that, I need to put a 7 here. That gives us 14 hydrogens, but 7 oxygens. So now that's balanced. You with me? We're adding H2O such that the oxygens are balanced. I've ruined it for hydrogens, but this is how we get the oxygen to show up. We only had oxygen here, up here, so this is how we get some oxygen to balance this.
I think I'm just confused with the hydrogen.
This,
Yeah.
it came from nowhere. It came from
Okay.
nowhere. This really isn't a complete reaction. It just shows sort of the skeleton of the redox reaction. You could,
So why couldn't you just put like 7 oxygen without the hydrogen?
because this is where they come from for these reactions. They come from the water. We are introducing the hydrogen and the oxygen. We're just doing it systematically instead of just arbitrarily sticking them up there. The problem is the electrons aren't going to balance the way this is. This is the way to sneak up on the electrons and get them correct. I know it's not intuitive at all. It's hydrogen by adding, I think it's just H plus, H plus. So we can add some H plus here. I suppose we could do these 2 steps up here, but sometimes you have to do these separately. So splitting them out is a good start because you might need to add some water here, but you might need to add water up here if there's more atoms. Okay, H plus. So we've got 14 H's here, so we're going to go over there. So now we've balanced the oxygen and the hydrogen. You with me? Is it coming back to you? Did you do it this way? Did you break it into the electrons first? That's the next step here. Step 4. Balance electrons. Okay, so individually, she say individually, you can look at the steps on here, but I'm summarizing it here. All right. We have 1 iron atom that's 2 plus, and 1 iron atom that's 3 plus. So what I really want here is if you take an iron 3 plus 1 electron, you'll get an iron 2 plus. That's why I wrote it on the right side. Do you see that logic? I didn't write it over here because an Fe2 plus an electron would give us an Fe1 plus. So to make this arrow make sense, I needed the electron on this side. Because a 3 plus a negative is going to be a 2 plus. Follow that. Another thing to say, what I did here, if this wasn't there, the total charges on this side are 3 plus, and the total charges on this side are 2 plus. Another way to say what I did was I balanced the charges. So -1 plus 3 would be plus 2. So you think of it either way. It's really kind of the same thing. Oh man, I hope the video's still going. Yes. All right, now we got to balance the bottom line. Again, we can think about it as balancing charges, but you can also think, because we found out this was 6 plus. So you know those chromium atoms have to be gaining electrons to become 3 plus. So I know the electrons are going over here. So how many do we need? We've got a charge of 3 plus over here. We've got 2 chromium, so we have a charge of 6 plus over here. You see what I'm saying? I've got 2 3 plus chromiums. So I've got a total of 6 plus on this side. On this side, I have a total of 14 plus and 2 minus. So 14, 13, 12. I have 12 plus on this side. I can get that down to 6 by going 6 electrons. So one way to think of it is, I suppose the best thing to do is to figure out the oxidation number on this chromium, which we just figured out was 6 plus. And then think, how many electrons, single electrons do I need to go I've got 2 chromiums here. Do you see this? So I wrote them here. They're both 6 plus. I just figured that out a minute ago. I've got 2 chromiums here. Each of them are 3 plus. So if I do 2 arrows, how do I get from 6 plus to 3 plus? I have to add some electrons. So I've got to add 3 negative charges to get there. Same down here, I've got to add 3 negative charges. So I've got to add a total of 6 electrons. I'll go on this chromium so I can end up with 2 3 plus chromiums. So one way to think of it is find the oxidation number here, split them up into singles, figure out how many electrons get you one at a time. See what I'm saying? The other way to think about it is the total charges. The total charge over here and the total charge over here, you have to add 6 negatives over here to get them to balance. So we've got a total of 6 plus over here, and now we have a total of 6 plus over here. No charges from there, 2 of those. We only have 2 chromiums here, so Cr2. And then we've got 14 plus here. So 14 plus and 12. 14 plus. This was minus. That was plus. 6. Charges do have to balance. Do I have this balanced? Yeah, go with the first method. Go with the first method. Okay, starting over for this one. Do it like this. Find the charge on this chromium, which was 6 plus. And then go, okay, I've got 2 of those that are 6 plus. This was the first method I mentioned. And I've got 2 of these. And then think, What do I have to do to this to turn it into that? I've got to reduce it, so I've got to add 3 negative charges to bring the 6 down to a 3. And the same thing here, because they're identical, which means a total of 6 electrons. That's the better way to do it. I think we'd have to split all those out into ions to think about it as charge. So that's where I came from, 6 electrons. There's one more step. In some sense, too. Between reactions. One of the things, so now we're going to tie these two half reactions together by making sure we have the same number of electrons. Because however many electrons are gained over here have to be the same number of electrons that are lost over here. So basically, I'm just going to multiply through here by 6 to get them to balance. See what I mean? Meaning, I'm going to multiply all of this by 6. 6, 6, 6. And now these two balance together. Because the amount of electrons that were gained over here are the same number of electrons that are lost over here. And what you do, the last step, add these two together. There's two ways I could do this. I could cancel now, or I could go ahead and add them. But adding them is just taking everything over here I'm adding together, everything over here I'm adding together. Meaning now I'm going to write 6 Fe plus 6 electrons, negative, plus 14, plus this. And over here I'm going to go 6 Fe plus 6 E negative, plus 2 Cr3 plus 7 H2O. You could cancel the electrons now, but I'm just going to go ahead and do it to show you what I mean by add them. I'm just going to add all of this together and add all of that together. 6 Fe 2 plus 6 electrons plus 14 of those plus Cr2O7. Now I'm going to add all this together. 6 Fe3 plus this plus this. Electrons negative plus 2 Cr, I have this now, Cr2 plus 7 H2O. That's tedious but not complicated. Just combine them. I just combined all of this in one row. I combined all of this in one row. I used a plus sign where needed. Whenever you have a reaction like this, anything that's on both sides is redundant. You can cross it out. It's the same thing we were doing when we did total ionic reactions to reduce them down to net ionic reactions. Anything that's on the left side that's also on the right side, I can cross it off. And basically only here I can do that with is the 6 electrons. So now I have here's the unbalanced reaction. And after all our tedious work, we have the balanced reaction. You had a different way we did this? Did you do the electrons up here first? That only works sometimes. That's the truth. And what we've done is we've balanced this reaction under acidic conditions. But no one brings that up in undergraduate. Balancing it in basic conditions would be adding OHs, OH negative in different places with water. I think that goes deep enough for the subject for 1212. But not all cases can you ignore water and everything and just balance by the electrons. So that's why all the rules. The oxygen and everything has to come from somewhere. Yeah, let me do one more of these. This was, did I even say? This was example 4.7. So you can go back through this. But now I'm going to do check your learning. Part. Let's see if I can actually do this. So check your learning gives us that's the answer. Cl2 reacts with OH to yield Cl minus Cl. Make sure they don't bring up basic conditions. Okay, good. Okay, step one, split it into half reactions. I guess we have to do figure out. That is plus 5, so this is plus 5 minus 2, Cl is minus 1, this Cl is 0. And this is going to be plus 1 and minus 2. Yeah. Some of the Cl is being reduced, and some of the Cl is being oxidized. So, go. Cl minus goes from 0 to -1. We have to go. Okay, so we have separated it into oxidation and reduction. Sorry to feel wrong. oxidation and reduction, okay? Balance everything but hydrogen and oxygen. I need a 2 here. And a 2 here. So that balances that. And now balance oxygen by adding H2O. So now I've got 3 oxygens over here, and 2 there and 1 there, so that's 3 oxygens. Now I'll balance the hydrogens by adding H+. Balance the electrons. I need 2 electrons here. So each of these chlorines gets an electron and makes it 0. And over here, I'm going from 0 to +5. So this needs to lose electrons. So the electrons are on this side. That's right. Add electrons to the 0, and it brings these down to -1. Now, add electrons to this side. How many? I've got Cl2 to Cl5 plus, Cl5 plus. I'm really just doing this to see if I can do it. Like this as an example. So a total of 10 electrons has to come off here. That's 2 and that's 10. Multiply by 5. This gives me 10 there, 5 there. 2 times 5 is 10. I'm not coming up with the same thing they did.
You have 6 oxygen on the right side and only 3 on the left side.
6 and 3. So what should this be? If I got 6 there, so I think I have to put. Water does show up here. C0H. COOH. QCl balance that. 6 oxygens. Okay. That balances the oxygens, right? 5 oxygens plus 1 more, that's 6, right? hydrogens. We got 10, right? That's 10, that makes 11, so I have to do 11 here. Oh. I think they're doing this under basic conditions, not telling us. So I will find better examples of that. What else did I say I needed better examples of early on? Or was it in my other class? Okay, up to balancing redox reactions. Look at the PowerPoint and my supplement PowerPoint and see if you're okay with that much. Looking at a reaction, deciding whether it's a redox reaction, identifying the oxidizer and the reductant. If you can do that, then we can do balancing next time. If this book has left something important out, I don't even have to review it.